Hello everyone, welcome back. Today we're going to be talking about the expansion of the universe. So let's start off by talking about the guy that pioneered this new field in astronomy about cosmology and the expansion of the universe. His name was Edwin Hubble. And yes, the Hubble Space Telescope was named after Edwin Hubble. And he postulated that apparent brightness depends on luminosity and distance. Luminosity is just the intensity of the light. And he noted that certain types of stars always have the same luminosity. And so he used that to create stellar classifications. He assumed that there were these same star types in other galaxies as well, not just the Milky Way. He thought that if we have the apparent brightness of stars and the luminosity, then we can calculate the distance to the stars. He was right, and he used this formula to calculate the distance to 9 separate galaxies from this. So this plays into what we call the inverse square law, which basically says that the farther away you are from a point of light, the less intense that light is going to be by a factor of d squared, where d represents distance. So B, if we look at this equation here, where B represents apparent brightness and L represents the luminosity, we can see that B decreases by a factor of d squared for every increase in luminosity. We should know this. This is pretty trivial if you think about it. The farther away that a point of light is, the less brighter that it seems to the naked eye and to the observer. So let's talk about some of the stellar classifications that Edwin Hubble made. Um, he came up with some spectral classes of O, B, A, F, G, K, and M. And they were all sorted based on A, the color that they look like, B, their surface temperatures, and C, just some examples of the stars. So some of the most famous examples of orange or red type M stars were Betelgeuse and Antares. Some K-type stars are Arcturus and Aldebaran. Our own sun falls under the G yellow group, and so on and so forth. And Hubble created these classifications from the relationship between temperature and color brightness. So you might be thinking, how does this all play into the expansion of the universe? Well, it turns out there exists something called a Doppler effect, which says that movement affects frequency, be that of light or sound or any other propagative undulating wave. Movement towards the observer results in shorter wavelengths and therefore a higher frequency, and movement away leads to longer wavelengths and lower frequency. You can think about this using the example of an ambulance. If you've ever heard an ambulance coming towards you with its siren on, you can notice that its frequency or its pitch tends to increase as it's moving towards you, but as soon as it moves away from you, as soon as it passes you, the pitch and the frequency of the siren decreases. And that's pretty analogous to how light behaves in the universe. And astronomers use the Doppler effect for all kinds of different things. Let's talk about redshift. Redshift is one of the most important concepts in modern day astronomy, and it uses the Doppler effect. So basically, it says that the Doppler effect also acts on light from a moving object. Light moving towards the observer will appear more blue because bluer light has higher frequencies, and light moving away from the observer will appear more red, again because red light has lower frequencies. The different degrees of redshift ultimately helps prove the expansion of the universe. Basically, Edwin Hubble saw that different objects had different amounts of redshift, and the redshift that those objects had were constantly changing. And he put that information together to figure out that the universe was expanding because everything is constantly redshifting away from Earth. Or objects that are not in our galaxy were constantly redshifting away from Earth. Let's talk about Alex Friedman. He was another very influential astrophysicist, but one that doesn't get a lot of the attention that he deserves. He said that the universe looks relatively the same in every direction. In cosmology, this is known as the homogeneity of the universe. Um, that's only if you ignore the differences on the smallest scale. And he used this assumption to come up with three different models of an expanding universe. So this is much after the time of Edwin Hubble. This is much after the concept of an expanding universe has been the status quo in the astrophysics community for a while now. So the first model was the Big Bang slash Big Crunch model. He said that in this model, the universe starts with a singularity and ends with a singularity. Obviously, that singularity being something like the Big Bang before it exploded. Um, he said that the universe is around for a finite amount of time and that it will eventually peak in its expansion, and afterwards, after its peak, it will start receding. He argued that at one point the expansion of the universe will eventually be overpowered by the forces of gravity, and gravity will eventually pull the universe back together. Now, the second model of the universe is the open model. This is the one that most astrophysicists tend to live by to this day, and it argues that everything is moving or expanding so rapidly that even the gravitational attraction between points in space and time and pieces of matter can never stop the expansion. And this is an infinite period of time. This universe will never stop expanding and will never stop growing. And this is the one that most astrophysicists tend to use today. The third model of the universe is also open. Uh, and this one says that the universe is expanding just fast enough to avoid gravitational collapse. But eventually, at one point, the expansion plateaus. So the universe is still expanding, but it's just not expanding faster. The speed of separation gets smaller, but never gets to zero. And this takes an infinite amount of time due to constant expansion. So you might be wondering which model of these is correct. For that, we need to know the rate of expansion and the average density of the universe, and this can be determined by observing redshift. If the density is low and the universe is more spread out, that means that gravity is too weak to stop the expansion. However, density is high and the universe is a lot closer together, that probably means that gravity will stop the expansion. So there's these two physicists, Arno Penzias and Robert Wilson, who both jointly won the Nobel Prize for Physics in 1978. And they were using a very sensitive microwave waves detector, and they found that the background microwave noise was the same in every direction that they pointed it in. And this supported Friedman's argument of constant expansion. Bob Dick and Jim Peebles said that the microwave radiation was just very redshifted light from the early universe. And leads for uh, this opens itself to the theory that the Big Bang did actually happen. Um, so let's talk about some dark matter then. Dark matter is not antimatter. Uh, Basically, our galaxy must have a large amount of dark matter, even though we can't see directly. We know that it's there because of its gravitational attraction on the orbits of stars. We infer it is there because of its effects inside the galaxy clusters, and it affects the motion of the galaxy. If we add all this dark matter up, we still only have 0.1 of the amount required to stop the expansion of the universe. So basically, even with all the matter and all the antimatter, all the dark matter in the universe, um, expansion will still go on because gravity is just, in the grand scheme of things, gravity is just not that strong. If you want to learn more about dark matter and dark energy, I've talked about this in one of my previous videos. Another theory is the steady state theory. And the idea was that as galaxies receded from each other, new galaxies were created in the gaps between. And this would lead to a large-scale conservation of density throughout the universe. Penzias and Wilson, the guys that won the Nobel Peace Prize, indicated that the universe must have been much denser in the past. Thus, the steady state theory had to be abandoned. Now let's talk about Penrose and Hawking. They claim that imploding stars always became singularities, and this holds true even when time is reversed. And this could even be applied to the universe as a whole, because it implies the existence of a singularity at the beginning of time. And Stephen Hawking proved using this theory that the universe was made from a black hole, which is kind of cool. Um, that's it. Thank you everyone for tuning in. This has been great, and I hope you watch some more of my other videos. Thank you.